logarithms and differentiating logarithmic functions. A few general notes here. Some of the things that we're going to use today are what are called the law of logs, which essentially is how you can manipulate logs. So 2 logs added is the same as a log of a product. If you subtract 2 logs, you can combine them as a log of a division. And if you multiply a log by a number n, it's equivalent of the log a to the power of n. And we actually tend to use these rules going from right to left. Hopefully we remember this guy, that the derivative of a log function is 1 over x. And we actually proved that. And a couple of things that are helpful. If you want to differentiate a function that has a log in it, first see if you can simplify it before you differentiate. And that's going to happen a lot today. And secondly, many derivatives of log functions use a chain rule. And that's going to happen a lot today as well. So let's jump right in and start finding derivatives with logs. Here's my first function. I want to differentiate the log of something. Well, the rule is a chain rule. The derivative of a log of something is 1 over that something times the derivative of that something. And then you just basically try and tidy it up as best you can. And there's really not anything you can do with it, so that's it, finished. Now you could have a function like this. Now it also has a log in it. It has a sign in it. And it's going to be a chain rule. So it's a sign of something. So you want to find the derivative of the sign of something. It's 1 over that something times the derivative of that something. So it's 1 over something times the derivative of that something, which is this fella. And then you make it look pretty. And that's your answer. So these are pretty straightforward functions that have logs in them. And when you have functions that just have logs in them like these, you're going to be using the chain rule, right? The function of a function. So let's look at an example of a question where this rule works. I would like to find the log of 1 over x to the power of 5. Now, I could simply just do a chain rule inside a chain rule, and that would work. But can you already imagine that that's going to be pretty ugly and messy? Right, it's just got weird powers in it. So I'm not going to do that yet. I'm going to see if I can use these laws here to rewrite this in a format that's going to make the derivative simpler. So I'm going to make this nicer so I can do that. So 1 over x to the 5 can be written like that. Agreed? 1 over x to the 5 is x to the negative 5. Now, which one of these 3 laws, remember we're going to be going from right to left, could I use on this guy to write him down in a different way?
Number 3.
That's correct. Third one. Now, this guy is totally equivalent to this one, but this guy is easy to differentiate. It's finished. Do you see how easy it was to differentiate? Because we spent some time simplifying it, right? Writing it down in the way that would be more conducive to differentiation. Here's another example. You trust me, you do not want to differentiate that guy right now. Would you agree that you would end up with a chain rule with a horrendous triple product rule with some baby chain rules at the end? Plenty of places to go wrong. And even if you did that right, can you imagine how much effort you probably are going to have on style points at the end, trying to make it look good? Right? It would be a horrendous question. So let's not differentiate it right now. Let's see if we can write it in a different format. Any suggestions for which one of these three rules we can use on that? I'm trying to find the top of my pen. Dropped it.
That looks like rule 1.
It does, doesn't it? And you're right, it is. Okay, I'll find that later. So I am going to split it as log of this guy plus the log of that guy plus the log of that guy, right? Differentiating things that are added is much easier than differentiating things that are multiplied, right? I can do better. Hopefully you can as well. Is there anything I can do to this guy, and this guy using one of these three laws that might make it even easier to differentiate? Which one of these laws could I use on these guys?
Back to rule 3.
So you get, correct, you get 7 of these guys, 10 of these guys, and 3 of those guys. So 2 lines of algebra have turned the original horrendous log function into something we can work with. Right, now differentiate it. Right, 7 log of somethings. 7 over the something times the derivative of the something, which in this case is 2. 10 log of somethings. 10 over that something times the derivative of the something, which in this case is 3. And lastly, 3 logs of something, 3 over something, times, oops, that's an 11 there, times the derivative of that something. So what I get is 14 of these, 30 of these, and 6 of these. We're done. So a fair amount of work up front has generated a much easier derivative at the end. I'm trying to sell this technique, right? That being able to use these laws can certainly make your life a lot easier when it comes to finding derivatives. Agreed? So let's focus on some more examples of making something look different. This one is version 5 of the homework. Okay, I want that guy to look better, right? I want that guy to be something nicer. I've only got these 3 rules to work with. Start the ball rolling. Give me something to do.
Would you start with?
Would I start with?
Rule 3?
Not yet. I will use rule 3, but not yet.
Would you separate them into two logs, log or ln of x and ln of e to the -5th?
Right, so I'd be using rule 1 then. Agreed.
Yes.
Okay. Now, you were talking about, Sabrina, using the third one. Okay, I'm going to use it on the second term. Does anybody know what number the natural log of e is?
1.
So isn't that -5x times 1? Isn't that -5x? Some of you, for instance, might have known that the natural log of e to the -5x is just -5x and did that right away. Now that guy is hardly worth bothering about. Would you agree its derivative is baby? If I had left this guy and tried to differentiate, wouldn't this be a chain rule with a product rule with a little bit of another chain rule later on? Right? That would be a recipe for screwing up. Because the more things you do, the more opportunities, at least the more opportunities I have to screw things up. Here's the next one. Right, I'm going to differentiate it, but definitely not going to leave it alone. I would not want to differentiate that guy with a chain rule inside a chain rule inside a chain rule. I think it'd be a triple chain rule, that one. So give me a better way to look at this guy.
The power of 1/2.
I agree. Where do I go now? Which one of these rules?
Three.
Agreed. Rule 3. Okay, that's as good as that's going to get. Let's differentiate then. It's a half log of something. So you get a half over something times the derivative of that something. And the half and the 2t interact really nicely. And there's your answer. Short and sweet, right? Boom, boom, done. The derivative part. How are we doing so far? Okay.
I see another with trig functions, because the one you did, it seemed like the sign was just ignored.
Ooh, I
Really
hope
good,
I
though.
didn't. Oh,
I think you treated the sine function like a logarithm function.
I did. Yeah, I fixed the question to sort the answer. You're right. Yeah, I don't know, but I did that. Well, I did. I know what I did, but I shouldn't have done it. Yeah. I guess I'll put a sine one in just to show you then. Right, this is not one of these. This is just a kind of rewind to what I should have done the first time. It's a sine of something, so you get the cosine of something times the derivative of that something. So the answer to this guy would be the log, the cosine of the natural log of x plus 1 all over x plus 1. Right. Yeah. That's what you would expect to see if a sine and cosine or something was used with a log. So that was a side issue. So kind of did that as a quickie. Here we go. let's return back to questions where this process is important. You might look at that guy and think, you're stuck. There are two things added. There isn't laws about a log of A plus B turning into anything, because there isn't such a law. There isn't any rules for doing that. It does mean, however, that if we work on it, maybe we could still simplify it, right? Any suggestions for what I could do to that question?
Pull out the e to the x.
Now, do you see two things multiplied? Because that's what I see. And if you see two things multiplied, can't you separate them as a log plus another log? Maybe we can cut some corners here. What is the natural log of e to the x? What does it simplify down to? The natural log of e to the x. We did one already today. Look, I'm
One.
old. Yeah, well, 1 in x.
1 to the x, right. Sorry.
Correct. Yes, x. 1 to the x. Plus this guy. Oh, derivative. 1 plus that guy. See how easy the derivative was?
Wait, why is 1 to the x x?
That's not 1 to the x. It's x log e. So it's x times 1. So the 1 was 1 times x. Right? Are we good, Corwin? Yeah, if you're saying something, you're not making it
Yes.
skin. Oh, we're good, good. Okay, let's go overboard with the next one. Yeah, let's just, yeah, got it here. This is the last type of this kind of question where you rearrange it so you can differentiate it. If you look at that guy, he is a pretty ugly function. Would you agree that you don't want to do the chain rule right now? Because wouldn't that be a chain rule with a quotient rule with some square roots floating about? Oh God, could you imagine how ugly that would be? That would be a whole page and another page probably. So I'll take suggestions on how we could rewrite that guy.
Start with the second rule, so turn it into 2 minus, or ln, yeah. That.
Yeah, no, when you said rule 2, I pretty much knew what you meant. Agreed? What about the square roots? That's probably the next stage, right?
Turn them
How could
into
I-
fractional powers and use 3.
Okay, so a half power for that one and rule 3. Agreed. Okay, I think that's as good as that's going to get. Agreed. You can't really do much more now. So let's differentiate. Half a log of something gets you half over something times the derivative of that something. Take away a half log of something is a half over something times the derivative of that something. So you get 1 over this guy, 2 negatives make a plus, 2 over that guy. And we are done. So if you're trying to differentiate the log of something and the something is a little bit messy, there's a good chance that you could use some of these rules to turn into something a lot easier to deal with and then just differentiate. That's kind of what we've been doing for the last 5 or so questions.
Could you simplify the term on the right to 1/2 minus 2x?
Ooh, could you? Yes. Did I notice it? No. Technically, yes. Actually, you should, but we're good. So we're going to change tack now, and we're going to look at a process that's called logarithmic differentiation. So this isn't product rule, quotient rule, chain rule, anything rule. This is a process called logarithmic differentiation. It's going to use some things that we've already done. It's going to use these rules and implicit differentiation. And we are going to use logarithmic differentiation to help us differentiate some weird powers. Let's find the derivative of 4 to the power of x. Well, let me tell you who it's not. So can you imagine you're the first guy, right? Because there's a first version of everything, who was thinking, I wonder what the derivative of 4 to the power of x is. He might, or she might say, well, I know e to the x is e to the x, so maybe the derivative of 4 to the x, right? Maybe it's 4 to the power of x, but it's not. Well, maybe it's some kind of multiply by the power, reduce the power by 1 kind of deal. Maybe it's that, but it's not. So I'm telling you that, so you'll never do that, right? Now, what's nice about those is that they are easy. What's bad about them is they're wrong. So just because it's easy doesn't mean you should remember it. So you are now going to ingrain in your brain, never use those things, they don't work. What we are going to learn is how to find the answer using logarithmic differentiation. And here is step 1. Take the natural log of both sides. Guaranteed step. Just do it. It's going to, you'll see in a minute why that's a good move. Now, step 2. Simplify this side. Typically, you're going to use rule 3, but I've seen questions where rule 1 and 2 also get used. Now, you probably don't need this line, but I'm putting it in anyway. Isn't the natural log of 4 just an ugly decimal? It's like 2.98 or something, right? It's just an ugly decimal. So isn't that like 4x, 3.1x, 87x? Isn't it just a multiple of x? Right? Keep that in your thought process. And that's basically step 2 done. Here's step 3 coming now. Implicit differentiation. Differentiate both sides. Now, the reason it's going to be implicit is if you differentiate the natural log of y, don't you get 1 over y times dy by dx? What's the derivative of the natural log of 4x? If it was 2x, wouldn't the answer be 2? If it was 1.2345x, wouldn't it be 1.2345? It's the natural log of 4x, so what's its derivative?
Natural log of 4.
Yeah, that's why I was pushing that. It's just a number, right? 5x gets you 5, log 4x gets you log 4, right? Makes sense? Just a decimal. Now, remember the goal here is to get dy by dx, right? The derivative. So algebraically, what should I do next to get dy by dx?
Divide by 1 over y.
Or multiply by y, which is the equivalent. And you say, well, that's great. There's the answer, but the answer's got y's in it. I don't want an answer with y's in it. I want an answer with x's in it. So what would we do to change that so we now have x's? What would I replace the y with?
4 to the x.
Function of x?
Yeah, and the function is 4 to the x. Now, I don't know if you had guessed that or not, but do you know the derivative of 4 to the power of x is actually the natural log of 4 to the power of x? It's just basically a multiple of 4 to the power of x, and that multiple is whatever the number natural log of 4 is. Now, you might say, well, what about e to the x? You told me that the derivative of e to the x, in fact, you proved it to me, was e to the x. I mean, and e is just a version of this, isn't it? Just a 2.7128. Well, let's see what happens. According to this rule, shouldn't the derivative be the natural log of e to the x? Great. And what number is the natural log of e?
One.
So do you see that e to the x is just a special case? Now, won't 2 to the power of x just be the natural log of 2 to the power of x? 10 to the power of x will be the natural log of 10 times 10 to the power of x. Couldn't you just memorize it now that you've seen one, you've got them all? Does that make sense? So if I wanted to differentiate a number, a is a number, a to the x, won't its derivative just be the natural log of a to the x? That means I can now differentiate 5 to the power of x and 2 million to the power of x, whatever I feel like. Right, so I've added to my list of things I can differentiate. Well, I'm not finished yet. The reason why you need logarithmic differentiation is you sometimes get answers you don't expect. If you were guessing, conjecture is just a fancy word in math for guessing. If you were conjecting what the derivative of x to the x is, what do you think it might have in its answer?
10x.
Natural log.
So you have to have a natural log. Would you expect probably an x to the x in it? Would you expect a natural log of x? Would that be a possibility based on what we've seen? Yeah, it's actually wrong, but it's totally sensible. So what is the answer? Well, we've got to do logarithmic differentiation. Right, that's why you can't always say, well, I've seen it for numbers, so I could probably do it for x's where a number used to be, because if it was a to the x, that would work, but it's not a, it's an x. So take the natural log of both sides. Use rule 3. Okay, that's good. Now let's differentiate using implicit. The derivative of log y is 1 over y dy by dx. How am I going to differentiate x log x? What method will I use to differentiate x log x? Yeah. It's going to be f dash g plus f of g dashed. That's 1, leave that guy alone, leave the first guy alone and differentiate a log, and you end up with the natural log of x plus 1. Now, multiply both sides by y. Do you see that's typical? And can you see that you then replace the y by its original? Do you see that the answer was darn close to what you predicted? But there's an extra plus 1 that you didn't predict. And I don't think it'd be even reasonable to assume that you would have thought that that plus 1 was necessary. Would you agree that's kind of a surprise? That you actually have a plus 1 there. What the heck is it doing? Well, it's doing what it's doing because that's the answer, right? It just happens to be that, and you have to accept that that's the correct derivative, right? Cool. We can find derivatives of quite exceptional functions. So let's try one. How about sine x to the power of cosine x? That's like the ultimate version of weird. Would you agree sine x to the power of cosine x would be some really weird function? I know you have no idea. I'm not even going to put it into Desmos. You can do that yourself. You probably break Desmos, right? It probably would just have a heart attack trying to sketch it. It would be a horrendously difficult function. But nonetheless, we're going to differentiate it. I'm taking the natural log of both sides. I'm going to use rule 3, which is very common. Are you all happy with this becoming that? Think of it as a to the n log a, right? Think of that as being an a and this being an n, right? See where they go. That's essentially what rule 3 is telling us. Now I'm going to do implicit differentiation. This fella, because it's like the ultimate of ugly, is still a product rule. See what you get. If you differentiate a cosine, you get a negative sign, and you leave that guy alone. Plus, you leave this guy alone. And now you're going to differentiate the natural log of sine x. That's a chain rule, isn't it? Natural log of sine x. You get 1 over sine x times the derivative of sine x. So I get negative sine x, the natural log of sine x, plus cos squared x. I'll call that cosecant x. That way it's not a fraction anymore. Multiply both sides by y. And then finally, replace the y. If we didn't have logarithmic differentiation, I think you could spend your entire life guessing what the derivative of that is. Would you agree that this mess here is not obvious why it is what it is? Right. The only bit you probably could have guessed is that that bit's going to be in the answer. But would you agree all of this is kind of mysterious? Right. as a guess, which is why we need processes sometimes, right? We can't just rely on patterns.
Is that
Any
a cosine x above the bottom sine x?
Yeah, it's sine x to the power of cosine x. I was just running short of room. So that's sine x to the power of cosine x. And this is negative sine x, the natural log of sine x, plus cos squared of cosecant x.
Aren't we supposed to format stuff like the cosine squared x, cosecant x, like cosine x tangent x?
Yeah, that would work as well.
Okay.
Yeah, there can be trigs like that. Sometimes you can have 2 or 3 versions of the right answer. I mean, the one you just mentioned is just as pretty, if not slightly prettier than mine, but they're equivalent, so they're okay. Are we good? Let's change tack. Totally new kind of question. Still on logs. Let's differentiate logs that are products, just for completeness sake. So I want to do a product, a quotient, and a general, right? Kind of covered them, but just for completeness sake, let's do a derivative where you have to use the product rule, then another one with a quotient rule, and then a third one with chain rule. In this world, that's f and that is j. So the derivative is f dash g plus f of g dashed. Leave that guy alone, so it's x squared. That fella is log x. No, I didn't. I'm getting tired here, sorry. Differentiate that guy. Leave him alone. Leave him alone. Differentiate that guy. There we go. So we have 2x log x plus an x. And if I'm being pernickety, which I should be, style point says if you can factor it, you should. So there's an example of a product rule with a log in it. Would you agree that this question, that's no use to you, right? Isn't this just a quotient rule? You can't do anything to it, you know, just get stuck in there. Top is f, bottom is g. So it's going to be f dash g plus f of g dashed. Differentiate the log, leave the g alone, and oh, darn it in space. Let's try this again. I said it's a quotient rule. Why am I not doing what I'm saying? Differentiate that. Leave that guy alone. Now we're on the right place. Leave the first one alone and differentiate the g. All over the bottom squared. Now we have style point issues. No, you are not allowed to leave things like that because you just don't want to do the rest or whatever. You gotta make it pretty. If you multiply this, you get x. If you multiply this, you get 1 over x. And these two guys, you get that. And yep, we have a problem. Do you think, I know what you want me to leave it alone, but do you think I'm going to leave 1 over x on a fraction? Ain't gonna happen. How do you fix it?
You can pull that half out and then you'd be able to put the 2 on the bottom.
Half it? Where's that? That's not a half, that's an x.
Oh, sorry.
That 1 over x, I gotta fix it. Okay, here's a clue. I'm going to multiply by a special version of 1.
X over
S-
X.
Yeah. And what that's going to get me is x squared plus 1 minus 2x squared log x. And on the bottom, I got that guy. That's it. I took care of the 1 over x. We have we have this fellow. A chain rule. So I've done a product, I've done a quotient with a log in it. Let's do a chain rule with a log in it. In fact, let's do a chain rule with some logs of logs in it. Nothing you can do algebraically. It's a log of something. So it's 1 over something times the derivative of that something. So it's 1 over something times 1 plus 1 over x. Okay, so far so good. I've seen this problem before. I gotta fix it. How do I fix it?
Bottom by.
What was the question?
How do I fix this? How do I take care of the 1 over x?
Just multiply by x over x again.
Yeah. And once you see something a couple of times, hopefully you just put it in your little toolbox and you say, oh, I've seen that problem before. How did I fix it? So normal product, quotient, and chain rules with logs are the same product, quotient, and chain rules that you've used with trig functions and powers of x and everything else, right? They don't change any, right? Okay, you're probably going to get fractions because of it, and that might mean some algebra to deal with that. So let's find the equation of a tangent line question. This is our last question for today. That's not the one I'm going to do. There we go. We're being asked to find the equation of the tangent line to this log function at the point 4, 0. Well, if you want to find the equation of a tangent line, you kind of start by finding the derivative. Well, that's a log of something, so you get 1 over something times the derivative of that something. And then you use the derivative to get the slope of the tangent line by evaluating the derivative at the x coordinate of 4. So it's 2 lots of 4 take away 4 over 4 squared take away 4 add 1. And the answer is it has a slope of 4. Are we good so far? Find the derivative, evaluate the derivative at the x coordinate of 4. That's the slope of the tangent line. And then to finish, we use the point slope equation. So y take away 0 equals 4 x take away 4. A lot of 4's in this question. So far, so good. Right, now I won't do it. But different question. Can you imagine I've got a function and I find its first derivative, you know, maybe this one, right? How do you find the second derivative? If you find the first derivative, what do you do to get the second derivative? It's not meant to be a trick question.
Can you just use the power rule?
Well, not necessarily so. Wouldn't you just differentiate the answer? Maybe it'll be a power rule. Maybe it'll be a product rule. Maybe it'll be a chain rule. But don't you just differentiate the derivative to get the second derivative? So if you took any of the questions that we've done today and someone said, find the first and the second derivative, wouldn't you take your answer to the first derivative and then differentiate it? The chances are it will be really ugly. You know, the second derivative, right? You might have to use a quotient rule and a chain rule together, you know, because it's such a messy thing, but it's doable, right? You can find first derivatives that then give you second derivatives.